Righto, there's a worked example here, which is more or less a combination of linear transformation of graphs and also for modeling. And this kind of problem is quite common. It's a transformation of a cosine curve. And so, yeah, so there's quite a few of these around. They're a bit tricky, but they're probably worth um, learning and understanding because they're usually quite high tariff questions. So you could get your reward with these when it comes to marks. Okay, let's have a look. Express 65 cos theta minus 20 sine theta in the form r cos theta plus alpha, where r is greater than 0 and alpha between 0 and pi by 2. Give the value of alpha correct to 4 decimal places. City wants to, well, then he goes on to say the part B down here about building a large circular wheel. So this process that we're going to go through in part A is going to help us solve the rest of it. Now, so you recognize this possibly as something called the R formula. A name I don't particularly like because it kind of disguises the fact that really it is about well, linear transformation of graphs, and the fact that you can actually express a linear combination of sines and cosines, as we've got here, um, as a transformed sine or cosine curve. And in this case, we're going for a cosine. Same thing, really. It's just a question of how much you shift your curve. All right, so let's have a go at that. Right, so first thing to recognize is our cosine two-angle expansion. So if we expand that out, we're going to get r cos theta cos alpha minus r sine theta sine alpha. Well, r and alpha are basically constants in all this. So if we compare coefficients, first of all, of cosine theta, we see that 65 is going to be equal to r cos alpha. Okay, comparing this expression to that expression. And then and 20 is going to be equal to r sine alpha. So that's what we've got there. Right, okay, so now we've got two equations in two unknowns, so we can solve for r and for alpha. And if we divide one equation by the other, we're going to get tan alpha as 20 by 65, giving us alpha is 0.298 radians. I've given that to 3 decimal places. They just say 4 in the question, but I think the last one's 0 if I remember. And then if we use our sine squared cos squared identity, that's going to give us, sorry, square this, and that's obviously going to be equal to 20 squared plus 65 squared. Factorize out the r squared, then of course this in brackets is equal to 1. So r squared is equal to this expression here. And if we work that through, it's going to give us r equals, well, we can have it in third form here, but it's rather awkward to work with. So that's just been taken to a decimal, 68.021 decimal place. So our 65 cos theta minus 20 sine theta, which is what we started with in the question, we can express as 68 cos theta plus 0.298 to a degree of accuracy. Okay, so that is the sort of the linear transformation come R formula part of the question. Now it goes on to say a city wants to build a large circular wheel that has a tourist attraction. The height of a tourist on the wheel is modeled by the equation h equals 70 minus 65 into this expression. Okay, t is the number of minutes after the boarding. So we've got 65 cos 0.2t plus 20 sine 0.2t. So t is in minutes and the angle's in radians. Find first of all the maximum height of the wheel. All right, well let's have a think about that for starters. So the first thing we do basically is we're going to take our expression here, and from what we've done in part A, we can actually rewrite this as that. Okay, so that basically what we're saying is that our theta corresponds to 0.2 t. Okay. So if we then complete that equation, we've got h equals 70 minus 68 cos 0.2 t plus 0.298. Okay, and that's in meters. Right, so this part B asks you what is the maximum height of the wheel. Again, sort of very common thing to ask, and possibly the minimum height as well. So, so the thing to note here is we've got the cosine of something. Well, the cosine of something is going to vary between -1 and +1. Now, because we've got a negative sign here, the maximum value of h is going to correspond to when the value of the cosine is -1, because then we've got 70 times 68 times -1, or 70 plus 68, 138 meters. Okay, so that's going to be fun to be up at the top of that. Right, so that is that bit. The time for one complete revolution, part C. Now, the interesting thing with this question and some of these questions, they're sometimes asked in terms of absolute time. You know, what if the at what time will the person return to Earth or whatever. This isn't written like this. This is written time for one complete revolution. Part D, if we look at that, the number of minutes the tourist will be over 100 meters above the ground. So in actual fact, this shift here of 0.298 doesn't really make any difference to this. If we look at this, it's quite useful to draw these things out, give yourself a little sketch. This is a little bit small, but I wanted to get it all on the same page. So so you can imagine that the time for one complete revolution is basically the time between corresponding points on the cosine curve, so it doesn't matter how much it's been shifted. And this part D is the number of minutes the tourist will be over 100 meters above the ground. And again, that doesn't really make any difference how much we've shifted it by. The shifting really just kind of determines, you know, where you are at t equals 0. So, so if that is the nature of the any particular problem you encounter, then it's worth noting that really, because it gives you a bit of a simplification. Okay, so we've written here for C and D, the shift of 0.298 makes no difference because C and D are relative to one cycle. Okay, so I've made things a bit easier for ourselves then. Okay, so one complete cycle takes from 0.2t is 0 to 0.2t equals 2 pi. Why is that? Because, you know, at the point where this is forgetting about our shift, where this is 0 to where it is equal to 2 pi is one complete cycle. Okay, you might have to think about that for a moment or two. So, in other words, from when 0.2t is equal to 0 up to where 0.2t equals 2 pi. Okay, so the total, so that gives us t equals 10 pi, t equals 0 to t equals 10 pi. Okay. And that's 31.4 minutes set to the nearest to one decimal place. Okay. Right, then the last part is the number of minutes the tourist will be over 100 meters above the ground in each revolution. So you have to be careful with this. It's sometimes a little bit difficult to get your brain around, but if we solve for h equals 100, you could do this as in inequality. Personally tend to find it a bit more awkward like that, but so if we solve for that, then basically that's the point when the tourist is over 100 meters is sort of delimited by these points, which kind of find the points on the graph there and there. Let's say this goes up to 138 meters. There's hundreds around about here somewhere, or is it there or whatever? So it's between these 2 points, and so if we can find that distance between those 2 points, then that will be the time for which the tourist is above the ground in each revolution of the Ferris wheel. Okay, so if we solve for that, what we're going to just work that through, we're going to get cosine of 0.2t is equal to minus 0.44 to 2 decimal places. So if we take the inverse cosine to solve for 0.2t, our primary solution is going to be 2.03 radians. But then so that would be kind of there. But then the following one, applying our symmetry and periodicity rules, is going to be at 2 pi minus 2.03 radians. Okay, so those are our 2 solutions. So I'll be a little bit careful here that we get these 2 solutions and not this solution and this solution. So so just be careful there. Right, so that's going to give us t is equal to, well, 0.2t is these things. So if we multiply by 5, we're going to get 10.15 corresponding to this solution, and 10 pi minus 10.15 pi corresponding to that solution. So the time would be the difference between these two. So this time is greater. So we're going to subtract 10.15 from this. So in other words, it's going to be 10 pi minus 20.3, which is going to give us 11.12 minutes. So that is the time for which the tourist will be over 100 meters above the ground in each revolution. Okay, so it's going to be a big Ferris wheel. It's going to take half an hour to go around. Like the London Eye, really, that sort of thing. Which does take quite a long time to go around, and then the time over 100 meters is, some portion of that, which is that. Okay, so there we go. As I said, combination of linear transformations of a sine curve or cosine curve, and then we're actually modeling the height of the Ferris wheel by a sine curve, which we're then using our transformation for. So it's a combination of the two. So anyway, that's it really. So hopefully that has been useful, and next time.